All right, last topic. Okay, so what we just saw on the screen, and I'll have to re-record that at home tonight. My wife's going to love that. Because I'm going to have to get her to sit in front of me and I have to explain it to her, because I've tried doing these recordings into the computer. It just doesn't work. All right, so you need a human. Okay, so the last thing we're going to learn about today is something called power series. I got the power. Okay, so this is called the power series. 1 plus x squared plus x cubed, and so on. Right, which ends up being this sum. Now, notice that this now is a function. Well, it's not really a function because it doesn't satisfy the conditions for being a function. This is why we have to call it a power series. Right? But it still has all the things that we do with functions. That is to say, if I give a number, if I put a number in here, we're going to be able to evaluate this. So for instance, I can ask, what is the power series when evaluated at 1/2? Right? That would be equal to 1 plus 1/2 plus 1/2 squared plus 1/2 cubed. And what is this equal then? You guys should be experts at this. It's a geometric series. So what's its sum? This is a geometric series. R to the power of n for n equals 0 to infinity. Supposing that r is less than 1, what is this equal to? 1 over 1 minus r. More confidence, because Friday. This is one of the first ones I gave you. Okay, this is a geometric series. Now tell me what it sums to. Huh?
2. 1 over 1.
Yeah, 1 minus 1 over 1/2. Can everyone see that?
Yes.
Right, because if I could have evaluated this instead, right? This is going to be equal to k equals 0 to infinity 1/2 to the k. So please be comfortable taking these geometric series. You have to be quick. Okay, so this ends up equaling 2. Okay, so we can say that s of 1/2 converges. But here's a question. For what x does s of x converge? Can you tell me? For what values of x does this converge?
Smaller than 1.
Exactly. Right? For x smaller than 1, this will converge. Right? Because at that point it just becomes the geometric series. And we know that the geometric series is convergent for r absolute value less than 1. All right, so I was going to say, notice in this case, s of x is the geometric series. Okay, so we have a proposition here. We know now if x is less than 1, what have we discovered? If x is less than 1, then 1 plus x squared plus x cubed plus x4 and so on, that's equal to 1 over 1 minus x. So this is what we did at the very beginning of class. I plotted this for you, 1 over 1 minus x. And then I plotted 1 plus, oops, I missed a term here. That should be 1 plus x. I plotted that line, then that parabola, then that cubic, then that quartic. And every time I added one of these terms, we were getting better and better approximations for this function in this locality. Right? We have to be this close to 1 in order for this to be an approximation for this. But here, we can already pull it out. Right? this actually isn't too hard to prove. You just have to multiply through, and then you get everything here will cancel properly. Right? You'll get one of this with all positives, and then you'll get a negative x, which will make all of those negatives and jump the degree by 1. So all you're left with is 1. That's actually very easy to prove. Okay, so now I need to give you the definition for a power series. I'm going to do that on the other board. Okay, so this is what a power series is. And the good news is this really is the last piece of technology I'm giving you. Because the Maclaurin series and the Taylor series are just power series. And in fact, the Maclaurin series is just a special Taylor series, which is a special power series. So really, this is the last thing that we need to understand. Okay, so a power series, and we have some terminology here. We say it's centered at, now what did I use? Centered at x equals 0, so this is the simpler one, is given by this. Sum n equals 0 to infinity of a coefficient times x to the n. Right, so this is something that looks like this. C naught x naught plus C1 x1 plus C2 x2 and so on. Right, so this is what this is basically our definition of a polynomial, except now we're letting it run to infinity. Right, so these things are called monomials and these are called coefficients, right? So we can just call this the unknown. Right, but the fact that these are coefficients is important because I'll keep calling them such. Okay, so this is a power series centered at 0. I'm also able to shift these power series left and right, so this shouldn't be too surprising. So we also have a power series centered at x equals a. Right? So I can come up with approximations at 0, but I also want to come up with approximations at any point on the real line. And this is a Taylor series that looks like this. So we're going to go from n equals 0 to infinity. We're going to have a coefficient, but we're going to do that instead. Right, so instead of having a polynomial at x naught, x1, x2, we're going to have a polynomial at x minus a naught plus x minus a1 plus x minus a squared, and so on. It's like we've introduced a new sort of variable, which is allowing us to shift left and right. But anyways, you can also just expand this and it becomes a normal polynomial in just x's. But anyways, so we have we can center at a different point. So in this case, A is called the center, and these CI's are real constants, are called coefficients. Okay, so first example, this one should be easy. So for the series we just dealt with, this one, the 1 plus x squared plus x cubed, what's the center? 0. Right? Because I could also write this like this. Right? X minus 0 squared, x minus 0 cubed. Right? So that makes the center obvious. So this one has center 0. And what are its coefficients? 1. Are all 1. Okay, right, so coefficients, it's not too big of a deal. Now, the problem is you sometimes have to search for these coefficients because you won't be given the function in a nice form like this, where it'll be obvious. Sometimes you'll have to do a little bit of manipulation. So, here's an exercise for you while I wipe down the boards. I want you to tell me what the center and sum of the coefficients, and give me the pattern if you can, of this sum 1 minus a half x minus 2 plus 1/4 x minus 2 squared. Now I'll just give you the pattern. So this goes all the way out to plus dot 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 minus a half to the power of n x minus 2n. So I want to know the center and tell me what Cn is. Tell me what the nth coefficient is. Well, I wipe down the other board. Can I wipe down this too while I'm at it? Cool. Okay, so let's continue. So I gave you this sum, or actually, I should be saying this power series, which ends up being sum n equals 0 to infinity of minus 1/2 to the n x minus 2 n. Okay, so you should be able to read everything off this. What's the center? 2. Right, you can read it off here. This has center 2. What are the coefficients Cn? What is the nth coefficient here?
-1/2.
Well, to n, right? So if I started expanding this, right, you'd see the coefficients. Minus, plus, right, and so on, right? These are the coefficients here. And you can read them, right? If I give you something like this, you should be able to very readily read off the center and the coefficients. The center is this, coefficients are this. It's just that you may have to manipulate what I gave you to look like this, because this was nice. I could have pulled the n out, and I could have tried to simplify this a bit to hide things. So you may have to undo it. Okay, so now the question is, where does S of x converge? How do you think we could go about doing this? Okay, well, I want to point something out to you. I could rewrite this sum like this. Okay, so I'm going to bring everything into the same bracket, because everything's to the power of n, which means all I have to do is multiply this minus a half with this x minus 2. So that minus just switches this. So I get 2 minus x over 2. Now can you tell me for which x this thing converges? There's a reason I wrote that at the beginning of class. What kind of sum is this? Huh? Yeah, because this looks like a geometric sum. If I were to put x in here, this becomes geometric. And we know for geometric sums that as long as the thing inside here is a fraction, a proper fraction, we're off to the races. It'll be convergent. So we need here...
X has to be smaller than 2.
Well, no, it's what she said. This has to be, the absolute value of this has to be less than 1. That's the condition. Right? So this is convergent when 2 minus x over 2 is less than 1. Right? it's like all the same stuff that you've been doing, except now I've thrown in an x. Right? So now you're going to be able to find ranges where things converge. And this will be called the radius of convergence. They're just fancy new terms for stuff that you can already do. Right? So all this stuff isn't too new. It's just one extra thing, but you're going to be using all the same old tools to do this stuff. Okay. So how do I now resolve this? Well, I'll walk through it. So if we have that, we need that 2 minus x over 2 is less than 1. This means that we have that minus 1 is less than, oops, remove those now. 2 minus x over 2, which is less than 1. Everyone get me from here to here? Just stop me as, no. Are you trolling me?
It's the face again.
Huh? Yeah, it's that face again. What's the absolute value, right? So if the absolute value of x is less than a, we know that x is bigger than minus a and less than positive a. I'm just using that. Okay. Don't make me a meme. I'll lose it. I'm already a meme on like the CS message boards. Okay, so you get me to here? So now I'm just going to multiply everything by 2. You're going to get minus 2 is less than 2 minus x is less than 2. Now I'm going to, what do I have to do next? I think I have to subtract 2 from everywhere. That's minus 4 is less than 0. Minus x is less than 0. And then I have to multiply everything by a negative, right? Because I want minus x. So that actually just switches everything. Okay, so what do we see? We see that if x is in 0 to 4, s of x converges. Okay? So this is all you have to do with power series. Like now I'm just going to throw you an x. I'm going to ask you about the convergence divergence of these. And all you have to do is use old tools. And at the end, you'll just have to solve some inequality like this. Because you'll get, like in the ratio test, you'll get that the limit of these things have to be finite. And you can work that through inequalities as well. We'll do it. Is there an x for which a power series is always convergent? Is there always one value for which these power series will converge? What happens if I plug 2 into here? What happens? What happens if I plug 2 into here? It becomes 0. Thereby, everything is 0. So if I put 0 into here, you get 0. And 0 is convergent. So there's always at least one number that these power series converge at. The center. Right? So that's why we have to give it a special name. So these power series are always convergent at their center. So we always get that for free. Now the new question is how far away from the center can we move and still be convergent? That's called the radius of convergence. I'll write these things down for you. But I just want to give you the impression that these pieces of terminology make sense here. Okay? So check this out. So if x is between 0 and 4, that sum will converge. If I draw this on a number line, it's no accident that we have 2 here, and we go out to 0 and 4. Right? We have a center, 2. You told me what the center was. And actually, we can go out each direction 2 units. So we say that this has a radius of convergence centered at 2 with radius 2. Right? It has the interval of convergence 0 through 4. They're just a bunch of terms. But fundamentally, what I'm trying to say is, look, we need to be able to specialize, or we need to be able to specify which x's I'm allowed to put into this sum for it to be divergent. Because for it to be convergent. Because ultimately we want to use them as approximations to complicated functions, and if they're divergent, they're not useful. Right? We can't use divergent sums to represent stuff. Everything would just be equal to infinity. Right, so give that a stare. I think especially this kind of stuff may be uncomfortable, so you may need a little bit of practice working through inequalities. But just remember your grade school stuff, right? That if you have to subtract something from everywhere, you have to multiply everywhere, and if you multiply by something negative, then you have to swap. Just remember those. pieces. Okay. Okay, so what I should have mentioned here is that in addition to S of x converging, I can actually write what it converges to. So as long as x is in the radius of convergence, I could say S of x is equal to 1 over 1 minus 2 minus x over 2, which ends up being 2 over x when you work it out. Right, so I can actually tell you ahead of time. Right? And I'm saying as long as you give a number between 0 and 4, strict, that's going to give you the sum of the convergence.
Can we figure out the range since we have 0 and 4? Do we just plug in those endpoints and figure out where we'll start and end?
You're working backwards. I only wrote this after determining the radius of convergence. I actually don't know what happens at the endpoints. These are open intervals.
Okay.
Right, so I only know what's happening on the inside. We'll talk about that in a bit. That's a good nuance. We'll do one more first, just so we can practice more tools. Okay, so here is another power series. K equals 0 to infinity of k factorial x to the k. And I want to know where does S of x converge? Later on, what the hell is going on? Later on, I'll just be saying something like find the radius of convergence. I haven't defined that yet, but so I'll just phrase it like this. So what would we do here? If x wasn't a number, if x was an unknown, like what tools do you have here? Okay, name the tools you have. Okay, so we know about geometric series, we know about power series, we know about p series. We have the ratio test, we have the root test, we have comparison test, we have limit test. Right, so what do we usually revert to when we see factorials? Ratio test. Right, so when you see these factorials, you should think ratio, because the ratio is the thing that's going to help us like eliminate these. Don't get lured by that power of k. The ratio test will also deal with these powers of k. Right, so ratio test is normally your better bet, especially when you see factorials. Okay, so what does the ratio test tell me? State the ratio test. Okay, let's say summons, the terms, right? The ratio of consecutive terms has to be what? For convergence. Okay, so here I know that the kth term is what? K factorial x over k. So we're going to apply the ratio test. So first I need the ratio, the absolute value of this. Okay? So I'm gonna show you a fast way to write this. Okay? Don't write k plus 1 factorial ever. Right? That's a waste of time. This is what you should write instead. Just write it like that, k plus 1 k factorial. It saves you at least one step, which is meaningful when you're racing against the clock. Also for this part, don't write x to the k plus 1. Write x to the k. You're just adding one extra term, but this is going to make it super obvious what the cancellation should be. Right? This would have been your second step anyway, so just skip the first step. Right? Then underneath, I'm going to write what's the other thing. All right, k factorial x to the k. So that and that, this and this, we get that this is equal to k plus 1x. Okay, now as you said, we need it to be the case that the limit of k goes to infinity of k plus 1 times x is less than 1. So for which x will this work?
Zero.
Who agrees with him? tell me for what values of x will this work? Will this be satisfied? I'll make one lap, because this should be very obvious. What happens if I put a 1? What does the limit go to? Well, what's limit of k as k goes to infinity?
Infinity.
What happens if I put a 2? What happens if I put a half? Many of you probably are overcomplicating this. Okay, so first of all, if I work this out, you're going to get limit k goes to infinity of kx plus x. Right? Okay, so for any x, this is going to converge, right? Because you can't pick infinity. So forget about this. Really, the whole convergence is hinged on this. Okay, so k is going to go to infinity. So what does x have to be to make that less than 1? 0. So who agrees with him now? Good. Okay, so this means that x is equal to 0. What was x in this instance, in the new pieces of language that I've given you? It was the center of this power series. This isn't surprising. These things have to converge at their center. Okay, so this is bad actually. This power series is like degenerate, right? It only has one point of convergence, and that's at the center, right? So this wouldn't be very useful for anything because it's a sum that just goes to infinity every time we plug anything else besides 1 in it, besides 0 in it. Okay, but like this is how you would determine these things. I haven't given you a new tool. I've just given you a new object, and you're using the old tools on the new object. I guess it's the same ratio, root test, limit test, except you're going to be working with the unknown. And so in the end, instead of getting a yes-no answer, you're going to be getting an interval. For x in here, you get that. Okay, so not a very fun example. Okay, so I'm going to give you now a theorem called the convergence theorem. You don't have to memorize this. It just has to be said to you at least once. Okay, so if we have this, a power series, if S at this number, C, converges, C as in a constant, and that constant is not equal to 0, I guess really what I should be saying is C is not the center, then S of x absolutely converges for everything that satisfies this condition. Okay, so if I know that I have a power series that converges at x equals 2, then it's also convergent for everything between minus 2 and 2. Right, so that is to say, if you have center here and you know you converge out there, then you also converge over there as well, and everywhere in between. Right, so this basically is just a statement that allows us to move, to say, for us to be able to give statements like this, saying, look, I found it can go all the way to 1. I proved that it converges when it's less than 1, and actually it's going to converge at every point. And this is allowing us to move from one point to an interval of points. The opposite's true, by the way. Right, that if it's not in that interval, then it's going to diverge. Okay. So now I just want to specify what I mean by radius of convergence. We've already talked about it a bit. So I'm just going to borrow our old example. So we determined that this is convergent for x in here from 0 to 4. So we can just draw it like this on a number line instead and talk about its convergence, about its center, which is 2. It goes out to 4, down to 0. So for this, we say this has a radius of convergence 2, because that's the radius. Its convergence is centered at 2. And the interval for which it converges is everything between 0 and 4. As you mentioned, though, these endpoints are inconclusive. I neither know if they're convergent or divergent. Right, so we know that for everything inside the interval will be convergent. Everything outside the interval, we're going to be divergent. But the endpoints require their individual analysis. Right, you're going to have to go evaluate the power series, in this case it's 0 and 4, and then use all the tools that you have for normal series to determine convergence or divergence. Okay, so again, radius of convergence was 2. Interval of a convergence is 0 through 4, and the center was at 2 for that example. Here's another theorem. If you have some k equals 0 to infinity of a coefficient times x minus a to the k, what's the center of this? A. Right? So we know that S of A is convergent. Okay, so let's call this the power series S of x. So if this is a power series either, so exactly one of the following 3 things is going to happen. 1, there is R, a radius, positive radius, such that S of x diverges for x outside the interval. So this is just basically the algebraic way of saying that you're like outside of the interval. Sx converges for x minus a inside the interval. That means you're inside. And inconclusive, we don't know at the endpoints x equals a minus r, a plus r. Okay, so again, all this is saying is that if you have a radius of convergence, you're convergent inside your interval, divergent outside your interval, and at the endpoints, we don't know. Right? More analysis is required. Okay, that's the first thing that can happen. The second thing that can happen is that S of x is convergent for all x. What would be the radius of convergence on this guy if we're convergent for every x on the real line? So remember, we have a center. So this thing's going to be centered at A, and the radius says how far out in both directions you can go and still be convergent. So if I'm telling you for every x we're convergent, what's the radius? Infinity, right? So this one is an infinite radius of convergence. 3. The last thing that can happen is that for every x we're divergent, except at the center where we have to be convergent. Right, so S of x is greater than infinity for x not equal to a, i.e. So what radius of convergence is this? Oh, I wrote the answer. Yeah. 0, right? So you have non-zero finite radius of convergence, infinite radius of convergence, and 0 radius of convergence. So single point, every point, interval of points. Those are the 3 possibilities when we're dealing with these power series. Okay, so I'm going to write you some examples while I wipe down the board, or examples, exercises. I want you to tell me what the radius of convergence is, and the center, for some x to the k. Right, that's just the basic power series. For some minus 1/2 n to the x minus 2 to the n. These are ones we already dealt with, by the way. And then some k factorial x to the k. We've already done all of these. You should be able to, like we've answered these questions already. I just want you to now write it down. So I'm going to light some of these boards and we'll come back to this. So for each of these, I want the center and the radius of convergence. Okay, let's go through all of them. Okay, so for what was the radius of convergence for this? We did it at the beginning of class.
What was the radius?
Well, give it to me, radius, interval, picture. So let's draw a picture. I want to draw a picture indicating the x's for which this will converge. So what should I draw?
We used 1 over 1.
Well, don't do this again. We did this earlier in class. We determined that this is convergent for x, well, at least 0. We determined that this was convergent for the absolute value of x less than 1. When the absolute value of x is less than 1, this is just the geometric series. Right? So I can write it like this. Right? We have minus 1, 1, 0. Okay, so this is the picture of the interval of convergence. It's centered at 0. What's the radius? 1, right? Just don't make a common mistake of saying the radius is the diameter. It's half the diameter, right? So radius. Because we're always at the center and we can always go out in either direction. This one, the other one that we did, this one had a picture like this, right? Remember, we went from something like 0 to 4. It was centered at 2. So again, convergence inside, divergence outside, I don't know at the endpoints. But this has a center 0 and a radius of convergence 2. Right? Not because it's centered at 2, because that's a distance from 2 to 4 and from 2 to 0. Right, I should have picked a better example. And finally, we did this one, whose interval of convergence looks like what? This. Right? No width. Right? So it's an interval of convergence of length 0, centered at 0. So you're always going to have that property at your center. I'm just going to erase this because I don't want to start a new column. Okay, so another theorem. Right. I can simplify this probably. Okay, so we have if this converges in the radius of convergence, then, and this is actually really important and not intuitive at all, but I can say then for x in here that we have a function, right, equal to this. And in fact, the derivative of this function is convergent. In the interval as well. In fact, all the derivatives are convergent. Okay. You're looking at me like, why do I care about this? But think about it. So I'm telling you have a power series and that's convergent in a radius. Now I'm also telling you that, well, the power series can be treated as a function within its radius of convergence. The thing that was limiting it from being a function was the fact that functions aren't allowed to go up to infinity. Right? So I'm saying, look, between a minus r and a plus r, you can give me a number and I'll give you a number back. The amazing thing is that function can be, I can take its derivative. And that derivative also is an infinite series, but that infinite series has the same radius of convergence as the function before. Right? So if you can imagine, we're trying to use these in other disciplines like statistics, where we take something, we approximate it with a power series, and then we want to do calculus on it. Right? So basically, this is a theorem that just says you're allowed to take derivatives of power series, and things will be a-okay. So what's not fun is that it's not always so intuitive. That's how to take these derivatives, but in some cases it is. So if I give you, again, this standard power series, what is its derivative? Well, let's go through. This? 0, 2x, 3x squared, 4x cubed, and so on. We could do another one. It's going to give you, oh, I missed, why do I always keep skipping the x? 1 plus x, okay, I'll just do it again. That's weird. I have some weird prejudice to the linear term. 1 plus x squared plus x cubed plus x fourth. That can be 0 plus 1 plus 2x plus 3x squared plus 4x cubed. You get 0 plus 0 plus 2 plus 6x plus 12x squared and so on. Right, but we didn't actually have to do it like this. I actually can just take the function in its sum form. So in this case, it'd be k equals 0 to infinity of x to the power of k. And I can just take the derivative of this. And how do I just take the derivative of this? Well, it's going to be the sum of k times x to the k minus 1. But notice something. What if we lost? Like, what does the index have to start from?
1.
Can I start from 0? No, because that would be a negative. Right, so I lose the first term. Right, because that's the one that was zeroed out. And if I do it again, you're going to have to start from 2. If you do it again, you're going to have to start from 3. Right, because a lot of these terms are just disappearing because they're constant. Right, so just know that you're able to take a derivative of something of these sums. And you should have some practice. Okay. Okay, so a little warning. This is very special. Right? This only applies to power series. If I give you this series, n equals 1 to infinity of sine n factorial of x over n squared. For homework, I want you to show that this is convergent. I'll tell you what it's convergent in. It's convergent everywhere. So it converges for x in here. Okay, what's its derivative? What's the derivative of that function? It's easy. Right, so we have the sum. What's the derivative of sine n factorial x?
Cos n factorial.
Yeah, cos n factorial x. Oh, n factorial x n factorial over n squared. Now, look what term we popped out. An n factorial. That's bad. That's going to make this way bigger than this. And in fact, this is divergent. Okay? So I told you that you can have a power series and the radius of convergent is invariant, unchanging, when you do derivatives. That's only true for power series. Right? Here's a counterexample. Here's a power series that is convergent, whose derivative is divergent. Right? So thereby, this isn't a power series. Right? I can't ask you for its coefficients. It doesn't have them. Because coefficients are only things that live in front of things that look like x minus a. Savvy?
Well, when you found the derivative, you just forgot about the n squared. Don't you have to use the quotient rule or something?
I'm taking a derivative in terms of x, not in terms of n.
So if we see a factorial, it's not a power series?
What can someone define a power series then? It's one of the first things I defined. This is a power series. That's a power series, and only that is a power series. This doesn't fall into that pattern. Well, like how can I, like, in sine's not even allowed. This has to be a constant. This has to be like a number. It can be a very complicated number. I can say, fine, like let sine give the coefficients, but that's the only place an x can be. Does everyone see that this does not fall into this pattern? Right, we're basically dealing with polynomials of infinite degree. You can think of it like that. We're not even allowed to divide by something. It's just a polynomial. Right, so anyways, these are not power series. That is a power series, and only that is a power series. It's because we're taking x to successively higher powers. That's why it's called the power series, right? Okay, what else do we have? Okay, so we talked about taking derivatives of power series. We should try to talk about the integral of power series. So if I know that I have this power series, n equals 0 to infinity, Cn x minus a to the n. And suppose that this guy has a radius of convergence in here, right? For r minus a, r plus a, like which basically is this picture. We're at the center r, and we go out to here. That's a plus r, and it's a minus r. That distance is r. The integral of this thing exists. And it's just going to be the integral of what you would expect, right? This is going to be the sum of n equals 0 to infinity of the integral of this. So it's Cn x minus a n over n plus 1. Oh, n plus 1 over n plus 1. And what do I do when I integrate? What do I have to add? Plus c. I'm going to call it big C, script C. Well, because I used C already, so I want another constant name.
Plus f.
Okay, f, right? F is a constant. Okay, so tell me if this is, can this converge? Yeah, this is now the antiderivative. So we know that convergence is preserved as we're taking derivatives. Are they preserved as we take integrals?
Yes.
No. Very obviously no, too. Right? Well, let's look at this. Why can I conclude immediately that this is divergent? suppose that this f isn't 0. What happens?
We're just gonna get bigger.
Yeah, we're going to get an infinite amount of f's. Okay? So as soon as that constant is non-zero, which it may be, there's no rule that says that these things are 0. You can get a non-zero constant, then it will diverge. Okay, so this is usually will be divergent when f is not equal to 0, right? So we can't take integrals and preserve convergence, only derivatives. Okay, so here's a question. Suppose we wanted to numerically, how could we numerically compute log of x? Right, because log of x is something we define to be the inverse of the natural logarithm. Right, but what happens if we actually wanted to say what ln of 4 was? How would I actually give you back a number from that? How does your calculator do it, for example? Your calculator doesn't have a big table. It doesn't have a lookup table to say, oh, ln 4 is stored here and it's like this. Right, your calculator has instructions to calculate these things. So I'm going to develop the instructions for numerically computing ln, which is basically why we have these power series. Because we have no other way of computing ln. I could just add and multiply things. And that's what are nice about these power series. All these power series are instructions about how to add and multiply stuff. Right, so I could tell a computer how to add and multiply. So I'm going to show you how to numerically compute ln. All right, so first we're going to start here. So notice, I'm going to give you a power series. 1 minus t plus t squared minus t cubed plus and so on, which is equal to the sum minus 1 to n t to the power of n, or even more compactly, minus t to the power of n. All right, when does this converge?
When minus t is smaller than...
When the absolute value of minus t. Okay, so this is convergent when the absolute value of minus t is less than 1, which means t has to be within minus 1 and 1. That's pretty obvious. All right, so we're going to be convergent when this is between minus 1 and 1. So for x in minus 1 to 1, we have that. Did I give this a name? Let me just call this the power series. We have that s of x is equal to what? 1 over 1 minus t? Yeah, plus t. Okay. So provided that x is in this interval, this power series is approximated by that equation. All right, so soak that in. I got to wipe down these boards. Okay, and notice that the derivative of ln of 1 plus t is that. So think of how you could use that fact now to develop an equation for calculating approximations of ln. Okay, so I'm going to do something that's going to look like the fundamental theorem of calculus, but it's not the fundamental theorem of calculus, what I'm employing here. So to approximate ln, we're going to do this. Right? So I know that sum of minus t to the n is equal to 1 over 1 plus t for x in this interval. Okay, so we also have that the integral from 0 to x, and I'm putting an x there because I'm trying to develop, I want to be able to come up with an approximation for ln x. So that's what this x is going to be, the x for the ln x. This is 1 over 1 plus t dt, okay? But we're talking about how these integrals and derivatives relate with power series, and I am actually allowed to at least take derivatives. Right, so what derivative gives me this integral? Well, we can take this. It's not arctan. It's too complicated.
Ln of something?
Yeah, it's ln of 1 plus t. Right, I just did this because I'm trying to get a ln x. Okay, so if I resolve this, I'm going to get ln of 1 plus x minus ln of 1. That's 0, thankfully. So this is equal to ln of 1 plus x. Savvy? This means that ln 1 plus x is equal to, what was the series? I think I may have missed a step. But that's fine, we can recover. All right, so I have to do this one in a different way. Okay, so we know that the integral from 0 to x of this is ln 1 plus x, but I can also work it out in a different way. I know that the integral from 0 to x of 1 over 1 plus t dt, I can use the approximation we have for this now, which is this. I can say that this is equal to the integral from 0 to x of 1 minus t plus t squared minus t cubed and so on. Okay? We have that. We know that this is approximated by this, or in this case, that this is approximated by this, right? So these two integrals are equal. Well, I can also work this out. This is going to go to what? T minus t squared half plus t cubed third minus t fourth over 4 and so on. We're going to have to take that from 0 to x, which ends up working out to x minus x squared half plus x cubed third minus x fourth 4, and so on. But now I know, okay, so this is now equal to this. So this series here is equal to ln 1 plus x. Right? So I did two integrals, the same integral. The first integral, I just used what we know about 1 over 1 plus t to get ln. The second integral, I'm converting this to a power series and integrating the power series instead. And what do I get? Well, I get this statement down here, right? That ln of 1 plus x is equal to the sum, and let's see if we can write this. K equals 1 to infinity of x to the power of k divided by k, and we should start at k plus 1. Okay, so ln of 1 plus x is equal to this, which means ln of x is equal to, I just have to substitute, okay, well I'll put a y in here just to not confuse everyone. I'm going to take x and I'm going to substitute y is equal to 1 plus x, which means that x gets y minus 1. So if I put y minus 1 in for x, you're going to get ln y. I got to put y minus 1 into there. K equals 1 to infinity minus 1k plus 1 y minus 1 to the k over k. Okay. So I know it just feels like I've been doing mathematical masturbation. But consider this. I used what we've learned about power series today to talk about a function ln, which is considered a special function. It's special functions because you know how it looks like, but I very much doubt if I say what is ln of 1.2, you would be able to give me a number for that. Right? You would have to go to a calculator. Right? But then it begs the question, how's the calculator doing it? Right? Someone at some point needed to be able to say this is how we get numerical approximations to ln. Well, look, ln of y is equal to this infinite sum. Right? I can sit down and multiply and add things together. This is just an instruction about adding and multiplying stuff. And we don't have to go to infinity. I can go to 100 million. And that's going to be a sufficient approximation for ln. Right? So this basically is how your calculator computes values of special functions. Right? We determine a power series for it and use it instead.
Are we supposed to know how to do that, or was it one of those proofs that just...
Well, this is not a proof. This is why power series are useful. This is why I'm showing it to you. Right? And yes, the answer is yes. But I'm going to tell you, you're not going to have to develop it like this. This is actually called the Taylor polynomial. Right? And there's a generic pattern that we can just exploit. Right? So this is an observation, but I'm going to give you the general method of doing it. I'll show you. We're going to actually, this is actually my example for doing Taylor polynomials. I'll show you. We'll get a Taylor approximation for ln, and it'll be way easier. Right? But I'm just saying we already have the power series technology to do this. Right? So when I do Taylor series, don't treat it as something new. It's just, okay, we've noticed that we can do this with power series. Now let's just write it down. What are exactly the steps that we're going to have to do? But otherwise, why are we playing with these infinite sums? Right? There has to be a reason. And the reason is because we need to be able to come up with the numerical approximations for special functions, or for things that are just weird. Okay, that probably wasn't the funnest. Okay, so I'm going to do, how much time do we got? Half hour? Okay, I'm going to write down I'm going to write you down one exercise, and the full solution is in the notes. Okay, so I'm going to write that up here, and then I'm going to wipe down the boards. And then we're going to do Taylor polynomials. Okay, so here's your exercise. Again, go to the notes. Here is a power series. Find interval of convergence. As in, tell me what x is, this will converge. Find a closed form for the sum itself inside its radius of convergence. And then repeat for the derivative of s. Okay, so that's a little bit of homework for you. It's actually quite simple. Okay, very, very last topic for this course. And then you never have to do math again after Friday. I really hope you guys pass.
That's up to you. That's up to you.
No, it's up to you. It's up to you.
He's working it.
I can't give you marks for things that are wrong. remember, it is up to you
We
to
will
pass
do
or
that,
not,
don't worry. We will.
right? And I really do hope that you guys get better than the outcome that you want, because you've worked really hard. And I really hope that all that effort turns into like a good outcome. I really do. So good luck to you guys.
Thank you.
Like I really feel for you. There's not a lot of time to study. But I'll be here all Thursday. But like really, good luck to you guys. Like I really would make me so happy inside
Say
if
it
I
one more time,
never
I'll
had
believe
to
you.
see you ever again in one of my
Say
classes.
it one more time and I'll believe you.
Good luck, really, 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 really good luck, right? Okay, I take it back. Now that make me proud, guys. You know, when you get a bad class, it like takes the life out of you. It makes me depressed for years. You guys weren't a bad class. Don't let it go to your head. My students in Vancouver were terrible students.
You do.
Okay, Taylor series. Okay, so we use Taylor series to give polynomial approximations to arbitrary functions. I really can't emphasize enough why polynomials are so nice, right? Polynomials are simple instructions about adding and multiplying stuff together, right? These are what computers are designed for, this mindless execution of a lot of arithmetic. I wouldn't be able to explain things to the computer in any other way. Like, how would you even begin explaining ln or sine to a computer? That's tough. Okay, so we usually explain them to a computer using these polynomial approximations. I showed you what those I showed you how they worked at the beginning of class. When I said here's a curve and here's another curve, which is going to be going to be successive better approximations to the curve. So now I'm going to just flesh out what I meant more precisely. Okay, so suppose we want to approximate f of x near a, or x equals a, right? Near a center. Right? These approximations aren't going to be good everywhere. It's asking for too much, but they will be good locally. So how do we do this? We would need a power series. We're going to call it P, x, such that, okay? So what should our approximation do? Well, the first thing I said was that, look, all of these functions look like lines when we look at them close enough. So the first thing that has to be true is the slope of our power series has to be the same as the slope of the function we're trying to approximate at the point. So I can write that like this. That the first derivative evaluated at a should be the same as the first derivative of the power series evaluated at a. Okay? If P was truly an approximation for f, it should at least have this property, right? That their slopes match. What's the next thing that we'd like? Well, we'd also like for our power series to have the same curvature at that point. We'd also like our power series, whoops, to have the same inflection, right? And it turns out we can go as far down this row as you want. And match that as well. These are all actually statements about curvature. First order curvature, second order curvature, third order. So I'm saying with every new term we add, we can account for one extra type of curvature. Right? So a power series of exactly one term would match just the slope. A power series of two terms will match the slope and the concavity. The third one will match the slope, the concavity, and the inflection. And we don't have names for the higher order stuff. Right? But this is basically the observation. Like, this is our desire, is to generate a power series with these qualities. So it's not actually too hard to work out what they have to be precisely. So the hardest part about these power series is just, or these Taylor series, is determining the nth derivative. Okay, so let's just write down. So an arbitrary power series looks like this. It's first coefficient, second coefficient. We're going to center it at A. Second coefficient, we're going to, how high should I go? To 3? Okay. So we take one derivative of this, and what does it look like? Well, 0 plus C1 plus 2C2 x minus a plus 3C3 x minus a squared. Second derivative is this. Well, 0, 0, and then this. So we get 2C2 plus 3 times 2 x minus a. I'm going to write the next term. That would have been 4 times 3, and we're going to have an x minus a squared. And one more for good measure. We're going to get what? 3 times 2 times, oh, I forgot my coefficient here. I forgot all the coefficients. C3, C4. This is going to be 3 times 2 times C3. And we're going to get 4 times 3 times 2 times C4, x minus a. What does the kth derivative look like? All I really care about is this leading term. What is it? I can give you some hints. So I can write, so C0 originally had the coefficient 0 factorial. C1 actually has the coefficient 1 factorial. C2 actually has the coefficient 2 factorial. This actually is 3 factorial. K factorial CK. Follow? This should be obvious. Every time you take a derivative of a monomial, like the so you have an x to the 7th, you take a derivative of the 7 comes down, then the 6 comes down, then the 5 comes down, then the 4 comes down. So at the very end, you have a 7 factorial. Okay, so I'm trying to devise a power series which has these conditions. But what do I know about P at A? What happens if I evaluate a power series at its center?
0.
Not necessarily 0, it's definitely convergent. It will hinge on what this coefficient is here, right? So all the other ones will disappear, and I'll be left with 0 factorial C0. If I evaluate the first derivative, what you end up getting is 1 factorial C1. Next, you get 2 factorial C2. If I go all the way and I do a kth derivative, you're going to end up getting k factorial C3.
C3?
Oh, CK. But we know that each of these need to match f. So this should be f of a. This should be f prime of a. This should be f double prime of a. And this should be f triple prime, f derived k times of a. Right, so now I can actually solve for these coefficients. Because if I just rearrange things a bit, we have that the kth coefficient of our power series should be equal to the kth derivative of f evaluated at a divided by k factorial. Right, I can actually backwards and solve for these coefficients, which means that at x equals a, around a, f of x is equal to, in some sense, the sum from k equals 0 to infinity of the kth derivative of f evaluated at a over k factorial And remember, these were coefficients, so now I have to add back in our unknown Taylor series. Right, so given a function f, you put it into this, and you get a power series, which approximates it. So you don't have to go through all that rigmarole we did on the last board. Right, you can just jump straight to here now. So what I'm going to do is going to go through the ln x exercise again, but we're just going to do this instead. Okay? So again, this is what we call a power series. Well, it is a power series, but it's called a Taylor series. Okay, so I'm gonna wipe this, and I'm just gonna write down some definitions for you, and then we're gonna use the forbidden board as my last hurrah as your teacher. Okay. How much time do we got?
20 minutes.
Oh, 40 minutes. Okay, we're good. 20 minutes. Oh. Definition. Taylor series. For a function f of x, its Taylor series at x equal a is this, what I just wrote over there. It's denoted usually by p. A equals 0 to infinity of the kth derivative of f evaluated in a, x minus a to the k over k factorial. Okay, that's a power series. Jesus, Murphy, yeah. Well, actually it's both, but yes, in this case, Taylor series. Definition of a Taylor polynomial, right, is just the finite sum over this. So a Taylor polynomial is denoted Pn of x, and that's just equal to k from 0 to not infinity to some finite n of the kth derivative of a, x minus a to the k over k factorial. Something irritating is when a is equal to 0 in a Taylor polynomial or series, it is called a Maclaurin series. Okay, so I've given you a bunch of equivalent names for the same thing, basically. We have power series, but we have specific types of power series called Taylor series, which are these. And there are even specific versions of Taylor series called Maclaurin series, which are just Taylor series centered at 0. Blame mathematicians for having egos. Because I'm sure it was the case that the Maclaurin's like, well, I technically was here first. Right, so it should be named after me. Right, so then we have these situations. But a Maclaurin series is just a Taylor series centered at 0.
So less work.
Huh?
So less work.
It's not necessarily less work.
Can it be, how is it more difficult than?
Well, I think they're equally difficult.
Okay.
Right? Well, in mathematics, you always, since we're allowed to shift things, it usually makes it convenient to locate everything at the origin. Right, so I'd say, okay, take this function, I want a Taylor approximation at x equals 9. Okay, well, just move everything to 0 and take the Maclaurin series instead. That's what they would do. But anyways, all I want you to know is that Maclaurin and Taylor are referring to the same thing, basically. Last example. Okay. Find the Taylor series of ln x at or near x equals 1. Okay, so what do we need to do here? Well, we're going to need to, so let's just call this g. We need to know what the kth derivative of g evaluated at 1 is. Right, so let's first try to get the derivatives of g. Okay, so what is the 0th derivative of g is ln x. The first is what? 1 over x. The second is minus 1 over x squared. The third is 1 over x cubed. The kth is equal to minus 1 over x to the power of k. Or am I off by a sign? No? That should work. Okay, so we have that. So really, but we have to be careful, because we have the kth derivative of g is equal to minus 1 over x to the power of k when k is bigger than 0. And actually, it is ln x for k is equal to 0. Right? So it's just all the terms fall into this pattern except for the first one, which is ln. And so I just have to be careful about that. Okay, so that means our Taylor polynomial is given by the sum from k equals 0 to infinity of f, well, in this case it's g, I suppose, evaluated at a over k factorial times x minus a to the k. So if I evaluate these things, what am I going to get? So first, we're going to have to pop. The first one's going to be special. So the first one's going to be ln x over 0 factorial x minus a to the 0. So really, this is going to just be ln x in the end.
Is that always the case?
What?
Where the first term with the
No, definitely not.
the original one?
No, definitely not. It's only because this ln turns into a rational polynomial after one step. Okay, so we got this, and then I just have to add the sum from 1 to infinity of what do we got now? Now we have, it's going to be minus 1 over a, all of that to the k, divided by k factorial, x minus, oh, and it's not a. What was it? We're doing this at 1, aren't we? So that should be a 1. This should be a 1. That's going to be a k. So I can simplify this a bit. This is going to be sum k equal 1 to infinity. This is just going to become an alternating term. So minus 1 to the k over k factorial times x minus 1 to the k. So I can write out a few terms of this. You're going to get ln x plus, let me think. You got ln x. Oh, but x was, okay, so you got ln x. That doesn't matter. The point is that from this, we can rearrange and say that ln of x is equal to minus this sum. So this is a Taylor series that's going to be an approximation for ln x near 1. And remember at the beginning of class how I showed you ln x and I came up with an approximation that was better and better and better by adding more and more terms? Those terms are coming from that series. And I just kept adding successively higher order terms. So any questions regarding that?
Will we always end up with an original term that we can move to the other side?
No.
So
No. Right. But if I give you a function f and say come up with the Taylor series, all you have to do is put it through that. That's it. That's what I want. I just want you to be able to do this. So all you need to do for a Taylor series is determine what the kth derivative of the function is. That's the hardest part. Once you determine what the kth derivative is, you're done. You just stick it into that equation. And then beyond that, you have to know what it is you have in the end. And you have a polynomial approximation to an arbitrary function near a center, the center being a. But really, practically speaking, you just have to find the kth derivative of the function. And then once you've done that, there's nothing else to do.
Any function with a k to the power of 0, wouldn't that be the original function? Because we're not taking the derivative of it?
Yeah, the 0th one will always be the original function.
So why is it that I said when k equals 0, you said it would?
Okay, so I suppose you are correct in that case. But I don't want you to think that you always have to do this rearranging.
So if we're finding the kth derivative, would we always say k equals 0, that's the original function?
Yeah, well, it's the zeroth derivative of the function, which is just the original function.
So wouldn't that mean we will always end up with it in there?
Yes, I already conceded your point, right?
Oh, sorry. I
Yes,
didn't
you're
get that. I
correct,
didn't
right?
get that. Okay.
But don't think that you always have to do this move. You don't,
No?
right? I shouldn't even have made it, right? Because you're just going to get the approximation when you do it, right? Because if you do this near 1, you're going to get 0 anyways for that one. Okay, any question? Okay, so remember, tomorrow is the work period. I'll be here. Like, bring work. Thursday, I'm going to be in my office all day long. And I don't like last-minute study, so I'm not going to be here on Friday. I don't know. It panics me as much as it panics you guys. But Thursday, here all day. I'm happy to help you. Use Piazza and get on your web work. And good luck. Godspeed.